Welcome and hello. This is a support video for HEC HMS. And in this video, I'm going to be talking about water capacity percent, snow water equivalent, and liquid water. I got a message from one of my viewers, one of you guys out there, asking about the liquid water, percent LW, and precip excess. These are three terms that are used in Part C of the HMS results output paths that are saved to DSS files. And in the first link in the video description is this page right here. It's the Part C descriptors. So we're going to see what that looks like. And those three terms that I was asked about are this one here, liquid water. This is the computed liquid water in the snowpack. The second one was right here. It's precip LWASS, the liquid water available at the soil surface calculated for a subbasin by a snowmelt method. And then the last one here is precip excess. It is at the subbasin incremental precipitation minus the losses. The second link in the video description is to this page here, selecting a snowmelt method. And then if you scroll down far enough, you'll get to the temperature index method right here. All right, so if you want more information about what I'm going to be covering, but quickly in this lesson, there's a good place to look. All right, what I have already set up for my HMS model is a single subbasin. And for that subbasin, I have a snowmelt method called temperature index. Loss method is initial and constant. Transform method is Clark unit hydrograph. And base flow method is linear reservoir. So if you want to look at these actual values, the initial and constant loss method is right here, going with 0.1 and 0.05. For the transform method, this is the Clark unit hydrograph. I'm going with 4 hours and 5 hours. And then linear reservoir, I'm using 2 layers. And then here are those parameters. All right, for temperature index, that's the type of snow method that's being used here. So let me go ahead and give this more space. I'm going with 32 degrees for both the PX and base temperatures, 0.08 for the wet melt rate and the dry melt rate. And I also wanted to direct your attention to this water capacity percentage right here. This is typically 3% or 5%. Sorry in advance, I don't have my second monitor, so you're going to see some of my notes here. That water capacity right here, again, typically 3 to 5%. It's also considered the maximum liquid water capacity, the amount of melted water that must accumulate in the snowpack before liquid water becomes available at the soil surface. So let's go ahead and take a look at the band data now. So within the snow method temperature index up here, if I expand that out, I've created one band. So this is sort of the initial conditions. This initial water content right here is starting off at 0. So that's an important one. And another important one here is I'm saying the initial snow water equivalent is 10 inches. So we're not actually even going to apply any precipitation in this support video, but I am going to show what it looks like when the snow melts, starting with 10 inches of initial snow water equivalent. And then as you've noticed, the basin model is called WC 10%. That alludes to what we're going to be changing here for this basin. And it's the subbasin snow method. It's this water capacity 10% right here. Okay, a few other things I got to show you around the model before we actually run it and look at some results. We have a meteorologic model. It's using specified hyetograph and specified thermograph. The hyetograph is nothing. There's no precipitation. So here's the precipitation gauge. Here's the precipitation data, 1 hour incremental inches. And then if I expand that, I've got the time window for the first 3 days of the year 2020. If I click on table, we just have 0 precipitation. And then there's the graph. Okay, what's a little more interesting is the temperature data. So I do have some data here. It's called 20-50. It's in Fahrenheit. It just ranges from 20 degrees up to 50 degrees every day, just oscillating at a 1 hour time interval. So if I expand that time window and then click on the table, you can look at the numbers here, but it's easier to digest those numbers by looking at the graph. The minimum temperature each day occurs at 6 a.m., and that's 20 degrees. 9 hours later at 3 p.m., that is the maximum daily air temperature at 50 degrees Fahrenheit. And that repeats day after day. Okay, I think that's enough for our introduction. Let's go ahead and run this simulation. So click run. Okay, so that's ran already. We can click on the results here and take a look at that data. If we click on subbasin 1, we can get some of the data here. But what I'm going to do is go over to DSS view. So let me open that up real quick. Okay, I'm going to go ahead and open up the file associated with that run, which is called water content 10%, and then click open. Here is all my data. I've got part B is subbasin, and then below that I have subbasin band. So subbasin 1, band 1. It's all the same because we only have one band for our one subbasin in the basin. But then here's that part C that I mentioned earlier in the video. The first plot I want to look at is the snow water equivalent. That's right here, SWE, and I click on the plot. Now, what we see here is it starts at 10 inches, which is what we initialized it at, and then it slowly starts to melt and it decreases down to about 9.15 inches by the end of the 3-day simulation. Now, it doesn't start melting until about early afternoon of the first day, and that's because the temperature doesn't actually increase past 32 degrees until this point, or maybe a little bit sooner. Let me go ahead and bring up that temperature plot once again. So just below it, we have the temperature plot. I can plot these together. All right, so in the bottom is the temperature, and this is just a 1 hour discretization. That's why it looks kind of choppy, but you can see the temperature of 32 degrees corresponds with just an hour or two before that snow water equivalent begins to decrease. Later, when the temperature drops below 32, we see a little bit of accumulation in that snow water equivalent. Okay, so let's go ahead and close that and then check out the liquid water right here, liquid water, and then I'll click on this plot here. This corresponds to the liquid water percentage in the snowpack. And as you can see, it increases from 0 because we initialized it at 0. And then it increases a little bit, mostly during the afternoon, decreases when it cools down at night, increases again in the afternoon. This is the second day. And then again, the third day, morning, and then afternoon, evening. At this point, I can tell you there's no excess. There's no runoff from the snowpack due to the temperatures and due to the high 10% water capacity. But if we set that water capacity to something more realistic, like 5%, for instance, then we're going to see a different looking plot, at least on days 2 and 3 here for this liquid water value. The last path I wanted to look at before we return to HMS is this value right here, precip-LWASS. And if I click on that, we have 0 runoff. Because remember, that refers to the liquid water available at the soil surface caused by the snowmelt method. Yes, there is water melting in the snowpack, but it's not enough to exceed that 10%. And hence, we're looking at all 0 values. Okay, let's go back to HMS now. Close that, minimize that. What I want to do is create a separate basin model. Let me click on components, and then here's basin model. Instead of 10%, I'm going to go ahead and right click, create copy, and then I'm going to call this 5%, and then click copy. Now, the only change I'm going to make here is click on subbasin, expand that, and then the temperature index. I'm going to scroll down here, change this 10% to a 5%, and then click save. Now, what I also want to do here is create a new simulation run. So here's the simulation run manager. I'm going to say new. I'm going to call it WC 5% and then click next. I'm going to use that new basin we created. Next, met model control specification, and that looks good. Okay, let's go ahead and run that model. Oh, okay, I need to set the meteorologic model. You know what? Before I do that, let me just go ahead and create the 3% as well, because that's what I plan to do. Create a copy. I'm going to name it 3% and copy. I'm going to make the same change now. So 3% subbasin, snow method, water capacity is 3%, and save. Okay, what it told me to do is go to the meteorologic model, which is MET1, and then click on basins, and then allow these 2 basins to use this meteorologic model. So those are now linked up, and I should be able to build the simulation like I intended to originally. Compute menu, simulation run manager. Okay, so this one is good to go. Let me go ahead and build the 3% one now. WC equals 3%. And then next, we're going to use the basin model that uses a snow capacity percentage of 3%. Next, next, and we're good. Okay, let me go ahead and save and then compute. I'm going to compute all at the same time here. So just toggle those on and compute. All right, so that's successful. Let's go check out our results in DSS view. Here we go, and I have the WC10 results already here. So let me go ahead and open up. Here's the 5% results, and then lastly, there's the 3% results. Let's check out the 5% results first. Okay, we have the snow water equivalent. This should look exactly the same, and it does. It starts at 10 inches. It goes down to about 9.15. Next, we're going to look at the liquid water path, and here's that data. Interesting, not quite the same shape as it was before. Instead of going up to 0.7 or zero point 0.8, whatever it is, now it has a ceiling of about 0.5 or 0.45. And what you're looking at here is actually the water capacity percentage times the snow water equivalent is serving as a maximum bound on this plot here. And the difference is going to be that precip LWASS. So you know what I should probably do? I'm going to go ahead and create a new DSS file, move the liquid water data for all three water capacity percentages to that file, and then I can compare them all on the same plot. Okay, so just work with me here. If you're new to DSS, that's fine. I'm going to just call this new DSS file results data. Sure. And then click OK. Okay, the file has been created. Now I'm going to go to my 10% data, and I'm going to select the precip LWASS, the liquid water, and also let's throw in the snow water equivalent. So I'm going to go edit, copy to, and then results data and DSS. Okay, I'm going to do the same thing for the 5% and the 3%. We don't need snow water equivalent again. It's going to be the exact same thing, but I do want liquid water and percent LWASS. Okay, so edit, copy to. That's going to results data.dss. Okay, thank you. And then the last one is the 3%. Here's liquid water, and here is percent LWASS. Edit, copy to, results, and OK. Okay, so let's go ahead and check out our results. This is the DSS file we created and then copied those paths to. So if I go view and refresh catalog, I now see the data. And take note, part F identifies what is the source. Did it come from 10%, 3%, or 5%? Let's go ahead and look at that liquid water part C first for all three, and then I'm going to plot it. So this is what I was expecting to see. In blue, this is 10%. This means there's no limit. Well, there is a limit, but it hasn't been reached yet. Green here is when that water capacity percentage in the snowpack is 5%. And so if the snow water equivalent is, say, 10 inches, then 5% of that would be half an inch. And that's why we're seeing the half an inch boundary is sort of serving as an upper bound. Now that snow water equivalent here, let's bring it up here. Actually, hold on. I think I can do this all in one view. Okay, if I highlight all those, click on the plot. Yeah, so the snow water equivalent starts at 10%, and then it's about 9.5 and down to 9. I'm going to bring up just these three together. This looks better. And then finally, the 3% here, 3% of 10 inches is going to be 0.3. And that's why at about 0.3 inches, we have what is an upper bound. So that constraint is active. And when it's active, that's when we have excess precipitation or runoff coming from the snowpack. Right now, I've got green highlighted. This is the 5%. It looks like there's just a little bit of deviation from maximum. I went back to my notes and realized it was precip excess that I was asked about. Okay, I got all three of those copied over. Let me go ahead and refresh my results data page. I'm going to click on View menu, refresh. Another way to visualize that upper bound would be to take the snow water equivalent, plot it, and then go ahead and multiply this value by 10%, 5%, and 3%. So I'm going to go ahead and do that. So snow water equivalent, let's go Tools, Math Functions. I do have a playlist on DSS View, and this is all covered. But let's see, I want to go ahead and go multiply this path by 0.1 for 10%. Compute. I don't want to save over. I want to save as a new path. So click this button. And then for part C, I'm just going to make something up here. This is not official, but I'm just going to call it SWE times WC. So that's 10%. Okay. Okay, a new record has been created. I'm going to do the same thing for 5%. So I'm going to click SWE, Tools, Math Functions, click this path, 0.05, and I need to set it to multiply. So just 5%, compute, save. Again, I'm going to type in WC, and then this is going to be 5% right here for part F, just so I don't get confused. And OK. OK. OK, last one here, snow water equivalent, Tools, Math Functions. Going to multiply that snow water equivalent by 0.03, compute, save as, times WC. That's going to be 3% here for part F, and click OK. OK, and close that. Now let's go ahead and plot these snow water equivalent and then some smaller percentages. Okay, so we don't need to see the original. Let's go ahead and take that out and then plot that. As you can see, the maximum snow water equivalent for 10% is almost an entire inch. But then for 5%, it's about half an inch. And then for 3%, it's about zero point 0.3 inches. And that upper limit decreases just a little bit as the 3-day simulation continues on. So if I could combine this plot right here, and I'm not sure if I can or not, with the liquid water, let's see what happens here and plot. Okay, so they showed up on different plots, but you can imagine, for instance, let's just look at 5%. That is the green line right here. The reason why it deviates from the blue line is because this yellow line down below here, if I was to put it on the same plot, and I kind of wish I could, it would actually be slicing off the top of that. It would be serving as an upper limit. And whenever this is an active constraint, then we're going to have runoff from the snowpack. So let me go ahead and isolate just this 5%. So just the green line and just the yellow line. That's this record here and this record. And then I'm going to actually open up the table. So file and then tabulate. Oh, this right here is the snow water equivalent times 5%, which serves as an upper bound for the liquid water. So if we scroll down to sometime in the middle of the second day, I'm trying to see where that constraint is active, and it looks like it occurs right here. Yes, this is where it starts at 8 p.m. on the second day, and it continues for as long as these two columns have the same value, which is right here. So it continues for 5 hours. For those 5 hours, that's when there will be release of water from the snowpack. On the third day, we're going to have a longer time period, I believe. Yeah, so that starts right here at 4 p.m. on the third day, and that continues all the way down through the end of the simulation and perhaps longer, but we stop the simulation after 3 days. So basically, we have about like 8 or 9 hours on day 3, about 4 or 5 hours on day 2, and that data should be reflected if I click on the 5% record for Precip LWAS and then click on the plot here. Here is the 4 or 5 hours on day 2 where we're getting some runoff from the snowpack. And then here's about 8 or 9 hours at the very end of day 3, which you can tell is actually a lot more volume and, of course, longer time. Anyway, I probably confused a few people, but hopefully I helped a few people as well, giving an actual example of using DSS View and HMS to build a model that addressed and discussed some of these issues: liquid water, Precip LWAS, and Precip excess. There's actually no precipitation in the model. So Precip excess wouldn't be anything. It's the incremental precipitation minus losses. And that's why if I click on Precip excess right here, and then click on the table, tabulate. Yeah, we're looking at all zeros here. Okay, there's a little bit of data right here, which I don't quite understand. All right, anyway, I hope that was helpful.